Okay. Any questions from last time? You may have had some time to think about it. Maybe I went a little bit fast.
So have you assumed that IR divergences have been removed? Suppose the amplitude had some IR divergences to begin with.
At the moment, I've ignored IR divergences.
Otherwise, it's a formal manipulation.
Absolutely. In some sense. However, yeah, good. So it's a well-known point that the soft theorem is formal because obviously amplitudes are IR divergent. But turns out that the AN plus 1 and AN are IR divergent in exactly the same way. So in some sense, at least in that formula, you can cancel the divergences on both sides.
I mean, this problem is there in 4 dimensions, but of course you consider 5 and higher dimension, this problem doesn't exist.
Yeah. So in tomorrow's lecture, at the end, when I'm going to write down an effective action, I'm going to write down an action that reproduces everything. IR divergence and soft theorem simultaneously. Everything will be derived in one go with that action. Anything else? Okay, so let me move on to gravity, and I'm just going to introduce the problem to you. But at the end of the day, the manipulations are identical. So what you have to do is, instead of starting with the Maxwell action, you have to start with the Einstein gravity action. You vary the action, you find, of course, equations of motion, then you have a bulk boundary term. You have to quantize that, you have to take that boundary term that gives you theta, compute omega, integrate over Cauchy slice, that gives you the gravitational phase symplectic form. And then you quantize the theory in exactly the same way that we went through with this in the photon case. So the calculations are a bit more tedious, but the method is exactly the same. So I just want to impress that upon you. I'm going to set up the problem for you, but then the hope is that you have understood enough that at least if you're ever interested, you can always go home and just do the calculation, because now I've told you how to do it. Okay, so the setup is simple. So now I'm no longer, so this was the metric of flat spacetime. I'm no longer working with flat spacetime. Now gravity is dynamical. The metric has become dynamical. And so, of course, my metric no longer takes that form. But in some sense, I want to preserve asymptotic flatness. So I definitely want my metric to become that when R is very large. So the real metric is going to be this plus subleading corrections in 1 over R. And the subleading corrections you can show, this is again an exercise where you have to consider the most general metric, plug it into Einstein's equations, solve it asymptotically order by order in 1 over R, and then you'll be able to find the exact most general structure for an asymptotically flat metric.
Why are we posing Einstein equations if we're showing overall metrics in the path integral, right?
No path integral right now. I'm just doing everything classically, and I'm going to quantize. But the nice thing about these methods is that everything I'm doing is on square plus. At the end of the day, if there's any higher derivative term in your GR action, it's not going to contribute. It's all going to fall off. So at the end of the day, only the Einstein-Hilbert term will matter anyway. By the way, maybe I should say this. This symmetry proof that I gave for you, if you did not know about the initial soft theorem proof that I showed you, that it was sort of the exact soft theorem which is true to all orders in loop, that proof over there was a perturbative proof, but it was an all orders proof in perturbation theory. At that point in time, we couldn't really say whether there could be non-perturbative corrections to that soft theorem. But now that we know it's coming from symmetries, we now know that that was also non-perturbatively exact. There cannot be any instanton corrections or anything else that contributes to that particular soft theorem. Anyway, so that's why this symmetry interpretation is so much stronger than just the Feynman diagram derivation that we did. Okay, so asymptotically flat metrics. Now, originally the structure of asymptotically flat metrics, people used to work in. I'm also working in Bondi gauge, but again, just like always, they used to take the metric on the sphere, on the asymptotic sphere, to be the round metric, which you can do. But I hate working with covariant derivatives, so I'm going to use this metric instead. It's still going to be flat asymptotically. Essentially, all the results that you can, if you read off BMS's original paper, is Bondi, Metzner, Van der Berg, whose name is never mentioned ever, and Sachs There are 4 authors, but you only say BMS for some reason. They worked on the metric where they have the round sphere. I'm just going to work in a metric where this is flat, just for simplicity. You can choose any metric in reality. It depends on slicing. Okay, so at leading order in large R, this is the metric, and then I have subleading corrections. So my subleading corrections in du squared. Oh, I'm still going to do it in 4 dimensions, and I'm going to tell you why I'm not doing it in any other dimensions. So there's some subleading corrections in du squared. Let me write everything down, and then I'll tell you what these things mean. That is everything you'll need. And of course, you can keep going, plus further subleading corrections. Okay, this line here, everything is 0 because this is my gauge choice. This is called Bondi gauge. So the gauge choice over here is that G R mu equal to 0. So that's why everything is identically 0 on this side. And then everything else is expanded in large R. So as you can see, the only non-trivial components, everything that's non-trivial is the CZZ, CZ bar, Z bar, then MB, and NZ.
This is after imposing Einstein equation.
This is after imposing Einstein. So you work in this gauge, you set GR mu equal to 0, write down the most general metric that you could possibly write down in this gauge, plug that metric into the Einstein's equations, and solve order by order in R. Up to the order that I've shown here, only the Einstein's equations, only the square root GR term contributes. Now if I add higher derivative terms to the action, that affects the subleading terms in the expansion. So those will all show up here, but in any case I don't care, because as I said, they will all drop out completely. We won't need any of them.
So also higher derivative.
Anything. Matter, you can add matter, do whatever you want. It will not affect any of these terms here, it will affect only these subleading pieces.
Was there be du dz bar?
Yeah, plus complex conjugate.
So is the sub or subleadings of theorems are sensible to the subleading part of the expansion, or?
The subleading soft theorem comes from there. There is a subleading soft graviton theorem, which does get corrected by higher derivative terms. That will come in here.
So this is why it is not universal, because it depends on which theorem you are.
Yes. So the subleading soft graviton theorem is not universal. The subleading and the leading soft graviton theorem, all of which come from the points I've shown you here on the board, they're universal. So it just comes from the square root GR term.
We fix the gauge fully, right?
Yeah.
So all these.
Small gauge. As always, I'm only allowed to fix small gauge. We have not fixed large gauge.
Well, I mean, this body mass and Z and CZ, they're physical degrees of freedom.
Yeah. Now let me tell you what the physical meaning of these things are. These are the gravitational degrees of freedom. Positive velocity, negative velocity. 2 degrees of freedom right there. That captures the energy of the gravitational wave or radiation in general. This is the angular momentum. So that's all the physical degrees of freedom. That's what they mean.
Can you repeat that, sorry?
This is called the Bondi mass aspect. So let's start with these guys. Gravitons have two polarizations in 4 dimensions. So there must be 2 degrees of freedom that label that data. That's over here. That's CZZ and CZ bar Z bar. So positive helicity is the holomorphic one, and negative helicity is the anti-holomorphic one. Gravitational radiation carries energy. The energy of that is measured by this coefficient here. That's called the Bondi mass aspect. This should be familiar to you. The Schwarzschild mass shows up exactly at this order with du squared. And then if your space-time has some rotational degrees of freedom, like at the Kerr black hole, for instance, then that is captured by this coefficient here. So this is known as the angular momentum aspect, the mass aspect, and these are the shear tensors. They capture the graviton degrees of freedom. Okay. Now let's talk about asymptotic symmetries in this system. So remember, when we were studying gauge theories, we were looking at asymptotic symmetries, and there the asymptotic symmetries were essentially large gauge transformations. In the gravitational case, the analog of gauge transformations is diffeomorphisms. So I need to look for large diffeomorphisms. I've already fixed my small gauge, so I'm not allowed to change the small gauge. So essentially, the set of all diffeomorphisms that preserves the structure that I've shown you on this board is what's called the BMS symmetries. So let me now explicitly tell you what that means. The equations that I need to solve, again, they're just scaling vector equations, so hopefully you can solve them. So the first thing I want to do is that I want to make sure that this gauge is preserved. I don't want to screw with that. So let's say this psi is the thing that generates BMS diffeomorphisms. GR mu has to be 0, identically 0. Not MB. G, let's say, so let's look at some, I'm just going to write down a few of them. So what am I allowed to do to GUU? The important thing is that we know that GUU has a 1 over R component, but of course MB can be whatever I want. So when I change GUU, it must change at order 1 over R, at best. It cannot change at order 1, because then it's going to affect the asymptotics, and the solution you're going to get is no longer going to be asymptotically flat. It's going to be a new phase space. So the Lie derivative of GUU needs to be order 1 over R. And in the same way, you can do all of them. Let's just do one more for just so we're on the same page. Let's look at GUZ. Can anyone tell me what GUZ, what I should write on the other side of that equality?
Something of the identity that's only with different coordinates, and then 1 over R.
Should be order 1. As long as it's order 1, it doesn't affect the boundary condition. Of course, it changes C. That's fine.
But C can depend on R.
No. Oh, sorry, I should make that clear. None of this depends on R. I've done a large R expansion. Everything depends on U, Z, and Z bar. Apologies, I should have mentioned this. Okay, hopefully you get the idea. Maybe one more. GUR. Anyone? What should I write here? 1 over R squared. Okay, so on and so forth. You can find a whole set of equations.
Didn't you only say outside GR is 0?
Yeah, my bad. Sorry, GR mu is not equal to 0. Of course, GR mu is not 0 because there's a GUR component. I meant to say GRR is 0 and GRZ is 0. Sorry. So I should GRZ and the Lie derivative of GRR has to be 0. Thank you for that.
Why can't you create some 1 over R contribution to GUR that would still be subleading compared to what the asymptote to be?
To GUR? No, the leading term is 1 over R square.
No, well, the leading term is up there, order 1.
No, I definitely don't want to touch this.
Yes, but you could have something in between the two.
No. That's if there could have been that, I would have put it in there. The claim is that this is to the order in R that I've shown. This is the most general thing that you can have. Now, if you were doing research on this, there are various ways in which you can weaken the thing I've written on the board. But this is the most well understood thing, and then of course you can play around in multiple ways to change things in some ways that you want. We're not going to do that. Okay.
Actually, even if you change the boundary conditions, there are no 1 over R
There's never 1 over r. In fact, you can change the order 1 term. You still cannot change the order 1 over r term. Yeah.
This bounding gauge, this is 3 metric components.
Yeah, so I forgot to write another. Notice that I have CZZ, CZ bar, Z bar, but I didn't write CZZ bar because there is another boundary gauge condition which is determinant of GAB, just the angular directions, over r squared del r. It's a really funny gauge condition, at least when I first saw it, but those days in the 60s, people used to think about it in terms of luminosities of gravitational waves and whatnot. And this determinant in the angular direction has to do with the luminosity of the wave. So they were fixing their gauge using these sort of physical conditions. But this has now become standard. Actually, from a calculational point of view, despite the fact that it looks weird, this is a good gauge to work in. It makes calculations really nice and simple. So by GAB, I mean just the angular directions. So you take that 2, 2 matrix just in the angular directions, and the determinant of that you fix to satisfy this property. In particular, what that implies is that this CAB matrix is traceless. So CZZ bar is equal to 0. Traceless, of course, I mean with respect to this matrix, this metric. But that tracelessness condition will not survive further down. So like you can have, like in this notation, people say C and then the next order is D, next order is E, and so on and so forth. Then you can have E, ZZ bar as well. Anyway, good question. So these are the four good point. Thank you for highlighting those things. Okay, so now here's the exercise. That's the metric, I've given it to you. You know how to compute Lie derivatives of a metric once you know that. Plug in that expansion into all of these equations and find the solution for psi order by order in 1 over r. That's an exercise for you guys. Okay. What do we expect? Let's start with what do we expect? Well, it's an asymptotically flat geometry. So in ADS, when you do this analysis, the isometries of ADS are the CFT group. So when you do the asymptotic analysis and you find the asymptotic symmetry group of ADS, you also get the conformal group. That makes sense. Far away, it becomes flat, it becomes ADS. So the same thing is true, it must be true here. So we are asymptotically flat manifold. So if I'm sitting very far away from any galaxies or anything, it's essentially completely flat as far as I'm concerned. I should find the Poincare group. I don't find the Poincare group. I find what's called the BMS group. So here I just wrote it down for you guys earlier in my first lecture. These were the exact isometry generators of Minkowski space. In this case, now I have corrections, subleading order corrections, but the leading order term takes exactly this form. Here also I have subleading corrections, but the leading order term also takes exactly this form. Except now, f is an arbitrary function of z and z bar, and yz is an arbitrary holomorphic vector field. Not the global SL2C, you have the full Virasoro, not the 4 translations, but infinitely many super translations is what they are called. Nothing to do with supersymmetry. This was discovered long before supersymmetry was studied. So this is the Virasoro, but so that we have the same language for this, we call this super translations, we call this super rotations. Okay? This puzzled a lot of people in the 60s. They did not like this at all. People tried their best. Essentially, a large part of the late 60s and 70s were spent trying to find modify the definition of this asymptotically flat spacetimes in some way so that you can get rid. Well, earlier in the 60s, they did not find the super rotation part. The super rotation is relatively new. They found the global SL2C. It's only after our understanding that it's studying local symmetries in a CFT is very interesting that this extension was understood. But in the 60s, at least, for them, what's called the BMS group actually so that you have notation correct. BMS group is super translations plus the Lorentz group. Then what's called the generalized BMS group is super translations plus super rotations. And then there's an extended generalized BMS group, we can super translations, super rotations, and wild transformations, but I'm not going to talk about that. Anyway, so people were really annoyed by the super translations, and they tried their best to change the definition of asymptotically flat spacetimes to get rid of them. And nothing worked. If you get rid of the super translations, you also got rid of some rotation part. It was never possible to reduce the BMS down to just Poincare and nothing else. And essentially because at that time they didn't really know what to do with it, they just gave up and said, okay, whatever, I don't care. And anyway, they didn't understand how to match scri plus and scri minus, so people didn't understand it, and that's when this entire research area completely petered out. And it wasn't until 2013 where Andy appreciated the fact that not only are super translations actually there, they're physical, and they reproduce for you the soft graviton theorem. So we should not be trying to get rid of them.
If you do the same analysis in ADS, you don't get this enhancement?
You get this enhancement in 3 dimensions, ADS3. The isometric group of ADS3 is the global SL2C, but the asymptotic symmetry group is Virasoro. So you get a similar enhancement, but only in 3 dimensions. In this story, you actually end up getting that enhancement in all dimensions.
How can I think of that? Why?
That is sort of expected. When you're doing asymptotic symmetry analysis, isometric group, you're doing transformations that keep the background fixed.
But that does not seem like the relevant thing to.
In gravity, we're allowed to change the background.
Even in ADS, we should be looking for asymptotic symmetry.
And it turns out you still get the conformal group. So that's a non-trivial.
Exactly.
Yeah, you work out there's an appropriate definition. You work out the asymptotic symmetry group. This is exactly the analysis you have to do there. And you end up getting, in that case, you still end up getting the conformal group. But here you get some nice enhancement. So this is just sort of the introduction I wanted to give you, and I don't have much more to say about this, because everything else beyond this requires tedious amounts of calculation. But I'll just tell you, point out the idea. So now I just tell you, one more point. Let me just make this point, because this often becomes a confusing statement. These are called asymptotic symmetries, but in no way are these symmetries approximate symmetries. They are exact symmetries of the theory. They're called asymptotic symmetries only in the sense that the action of these symmetries takes a nice and simple form out at infinity. This is the killing vector field at leading order in large R. It looks very simple. When you add these plus dot 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 terms and keep looking at the behavior of this killing vector field, it's not a killing vector field. It's this vector field at further subleading orders in R, it's a mess. It's a huge mess. Same thing is true here. Okay, these are all diffeomorphisms. Diffeomorphism is an exact symmetry of GR. All of these are exact symmetries of the theory. They're only asymptotic symmetries just in the sense that in the asymptotic region, they have universal global action. But inside, once you keep going inside, then it's a complicated mess. Okay, so just a point. Okay, so you do the same thing as before that we did in gory detail for the photon case, construct the phase space, look for canonical transformations, in this case these BMS transformations, construct the charges, and I'll just tell you what the charges are, and the charges turn out to be now PF, but now F is any function, not that special function that we had before. PF turns out to be the integral over scri plus minus. It's still a boundary term. Earlier it was integral over star F, and now this is integral over F times MB, which tells you that MB should calculate the energy. In particular, when F is 1, that's time translations, should give you the Hamiltonian. The integral of the Bondi mass aspect is the Hamiltonian, as we know. This comes from the ADM formalism as well. And if I work out the angular momentum, this also integral over scri minus gives you YZ NZ. So now telling you that this NZ measures angular momentum. Okay, so that's all I'll end there. And of course, this story, I wouldn't be telling you any of this on the board unless it was true that if you now take this, plug it into the S matrix, Ward identity, do all the things that I told you, this term derives for you the leading soft graviton theorem, and this derives for you the subleading soft graviton theorem. I haven't yet told you what the subleading soft graviton theorem is. It'll show up in tomorrow's lecture. I'll tell you exactly what that is. Yes.
So what happens if you do this asymptotic analysis on I0?
Yes. So back in the day, when people did that, they found just the Poincare group. And they were happy with that because that's what they wanted. Nowadays, now that we know that these symmetries are interesting and we would like to sort of find enhancements, there are lots of papers written, especially by Mark Hanot and his collaborators, who are studying these symmetry groups at I0, and they also find a similar enhancement. Yeah. What is the group called? SPRI group or something? What is the group?
Space like infinity. SPI.
SPI. It's called SPI group. It's basically just a similar enhancement.
Symmetry field just continue to the I0 part.
Yeah.
His name was given by Ashton already. Perhaps even by Hero.
Okay. Yeah.
The funny thing is that it's in principle is even larger than the group at null infinity because there are so-called logarithmic superconstellation of space like infinity, which people don't believe they are physical, but we don't know.
Okay. That's the end of my discussion for asymptotically flat spacetimes. It's the end of my discussion of sort of analyzing these symmetries from a space-time picture. Now I'm going to completely shift gears and analyze everything from momentum space. So starting from S matrices. So before I do that, questions?
Say logarithmic dependence, but like what is the smoothness condition we're assuming on this f of zz bar? What is the regularity condition on f
On the sphere?
of
Just a smooth function of the sphere.
smooth or real analytic? Do you want like a generators?
It has never mattered for any of the calculations I've done, so I don't know the answer, strictly speaking. It's never been an issue what the exact type of smoothness is.
Mod z square, log z would be fine even though it's not Taylor.
I don't think that's the type of log z terms that he's talking about.
Oh.
Is it? It's not log in f.
No.
You have other modes. So now these BMS diffeomorphisms are not just parameterized by f and y, then f, y, and now some other functions which are coefficients of the log terms. There are log terms in the expansion, which
Okay.
so there are other completely different modes. Okay.
They just come from like solving the Einstein equation.
Yeah. Okay, let us talk about celestial amplitudes. I have half an hour for today. So, as you saw, when I started doing explicit calculations, initially I started out trying to write down things in general sigma, completely general dimensions and general backgrounds. But then when I started doing actual calculations, I focused myself to d equal to 4. There's a good reason for that. We don't actually know how to do calculations in d greater than 4 in most cases. For the abelian, well, for the photon case, it was resolved by me in 2019 how to do the calculations in even and odd dimensions. Even and odd dimensions are very special. They're qualitatively completely different from each other, which we now know how to resolve. But asymptotically flat spacetimes, we don't even know how to define them. We don't even know what the correct definition of these things are in beyond 4, greater than 4 dimensions. Federico has much better idea, but there's in odd dimensions we really don't know anything. But in even dimensions we have some ideas, but nothing has been formalized, and definitely we don't even know whether superrotations. Remember, superrotations was just enhancement of SL2C to local SL2, to local Virasoro. But there is no such local group, local conformal group in higher dimensions. So you might think, oh, there are no superrotations in higher dimensions. But the ward identities, namely the soft theorems, they exist in all dimensions. So that you might think there must exist some definition of superrotations even in higher dimensions. That's also what I think, but we have never been able to work this out.
Do you know what happens with this word identity soft theorem correspondence in ADS?
There's no infinite dimensional symmetry group in ADS, so there's no infinitely many soft theorems.
So does something happen in ADS 3 or is it 2?
Yes. You have the large gravitons, boundary gravitons, and they have their soft theorem. This is essentially insertions of the stress tensor in the CFT side.
But in higher dimensional ADS there are no soft theorems.
In any case, there are multiple issues of the space-time thing.
Isn't this factor in 3 or in 2 dimensional?
ADS. I mean, there's topological degrees of freedom.
Indeed, I mean.
Yeah, but that's it.
Not trivial.
Okay. Anyway, despite the fact that I showed you many nice calculations in space-time, it's hard to do anything beyond what I showed you. You can try your best to weaken some of the boundary conditions, extend your phase space in 4 dimensions in some sense, but it's very hard to go beyond 4 dimensions. On the flip side, on the amplitude side, it's very easy to generalize to any dimensions, including odd dimensions. The structure of S matrix amplitudes doesn't care which dimension, for the most part, doesn't care which dimension I'm sitting in. So a much nicer approach, in my opinion, to celestial amplitudes is to start directly from the S matrix and then construct celestial sort of correlators from the S matrix itself. And that's what I'm going to show you how to do now. However, it's not, the things that I've talked about right now is not a complete waste. You might think, why did he spend so much time talking about this? We learned about the existence of these symmetries. And what I'm going to do now, from this point on, is to just use this knowledge that I now have, that we have BMS symmetries, we have superrotation, supertranslations, and use that to constrain my CCFT to the extent that it's possible. And we'll see that essentially by making the simplest possible, the stupidest guess, we'll always keep getting the right answers. We'll be able to construct the stress tensor just by guessing what it is, and it'll be the right answer. We'll be able to construct currents, we'll be able to resolve the whole IR divergence issue just by guessing the action, and it'll be the most simple action and it'll give us the right answer. So from this point on, we'll just be following our noses. Whenever possible, guess, do the stupidest possible guess and check whether it's the right answer, and it'll always be the right answer. So we put in a lot of effort to learn these things, and now I think it'll be really where we see the power of the symmetry structure that we have learned about. Okay, so celestial amplitudes. So in order to sort of motivate for you what the celestial amplitude is and why we should construct it in the way that we constructed, let me go back to this original construction that I did, where I constructed for you these creation annihilation operators, which were roughly the Fourier transform now I'm going to do work in general dimensions. There's no more need to sit in 4 dimensions. Some field taken out to sky plus, appropriately normalized. It's like in ADS you have to normalize with z to the delta, you have to remove that factor. So it's roughly speaking, the bulk field goes like 1 over r to the d over 2 times that operator phi. So this is like the z to the delta part of, so you extract out this coefficient, you take the Fourier transform, and you construct this object, and lo and behold, it satisfies exactly the right commutators of a creation annihilation operator. Again, we see the localization process in action. Here, x is a local point on this space-time sphere. Here, x is a point in momentum space, and they're equal to each other. And if I remind myself, this omega x was creating for me momentum which has the form omega over 2, 1 plus x squared, 2 xa, 1 minus x squared. So this is now the d-dimensional generalization of this. Okay, let's ask ourselves, how does this momentum transform under Lorentz transformations? So this is a momentum p mu omega x. Of course, you can check that this p squared is 0. Okay, how does that momentum transform under Lorentz transformations? In other words, if I take lambda mu nu p nu omega x, of course this is another null momentum, so this must also be parametrizable exactly in that way. but now with some different omega prime x prime. And the question is, given lambda, how can we extract what is omega prime and x prime?
We're doing asymptotic flat space.
Right now I'm going back to flat space-time. Now I'm talking about S matrix amplitudes, and even you can think of gravitational S matrices as well, but everything is in perturbation theory. So you take G, you expand as eta plus H, and then so the background is always Minkowski space-time, and then you can construct fluctuations and S matrices on top of that. So everything will be, however, there are lots of interesting stories about doing this stuff in black hole backgrounds, which I will not unfortunately have the time to discuss. Okay. So it's almost obvious what we would like to do is to find a map between Lorentz matrices and the conformal group. Of course, after all, we know that lambda is in SO 1 comma D plus 1, but this is isomorphic to the conformal group on RD. So if I can tell you what this isomorphism is exactly, if I can write that down for you, then of course you can go ahead and check this. You can work out what is omega prime x prime explicitly. Take that full lambda, plug it in here, compute the new p. Obviously we know it's null, so it must be, you can write it in this form and then solve some algebraic equations. Okay. I won't write out the full isomorphism, it's in my notes, but let me write out some of them. So there's so A lambda corresponds to scale transformations. There's a reason it's called A. There's this Gelfand decomposition of the Lorentz group, where SOD comma 1 is sort of decomposed into this M N tilde M A N. That's those are translations, rotations, scale transformations, special conformal transformations. It's just notation that mathematicians like to use. So whenever you have scale transformations, it's conventional to use A. Translations, you use N tilde. Rotations, you use M. And special conformal transformations, you use N. Anyway, so here's a matrix that'll do that gives us the right answer. 1 over lambda. Okay, so you can check that this is actually a Lorentz matrix. It has determinant 1 and it satisfies, of course we know it has to satisfy, so you can check that this satisfies that. And then you can also check that if I act with lambda A lambda on this P, I'm going to get a new P where the new omega is lambda is omega divided by lambda, and the new x is lambda times x. So in other words, these coordinates are really nice. I've only shown you one example, but this is always true. There's another example for translations, and when I do translations, the action is omega, it remains invariant, and then x goes to x plus a. So these coordinates are really very nice, because the coordinate x transforms exactly like the local coordinate that we expect in a CFT. So these operators that I've written out here must transform basically almost, as we'll see, like some local set of operators, which we can essentially just see by looking at how momentum transforms. And after all, we have already shown that these operators create particles with precisely this momentum.
So one thing, then the fact that you can match the x in momentum space and in position space allows you to do CFT in momentum space.
Yes.
Okay. So this is the way to define CFT momentum space.
It's not really, it's bulk momentum space, not the momentum space of the boundary CFT.
It's not a Fourier transform.
Not of the CFT itself. It's a Fourier transform of the bulk, which we are interpreting as a CFT on the boundary.
It's the position of the celeste of the
Yeah.
CFT that are towards the momentum in the bulk.
Yeah, yeah. Okay, so now that we have this as a hint, and maybe I didn't even need to give you this hint. I could have simply told you, because after all this is the creation annihilation operator. So one of the first things you learn how to do in QFT is to compute the Lorentz transformation properties of creation annihilation operators. So I could have just told you, tell me what the Lorentz transformation properties are. That's an exercise. But I hope I've motivated you to sort of, you can guess what it should look like. So let me now write it out, and hopefully you won't be surprised. So this operator O, when acted with TA, remember now my conformal generators were TA, JAB, KA, and D. These were all sitting inside of M mu nu. So at the end of the day, this is just the Lorentz transformations. So this is just del A of O. So this TA, so the X sitting inside of here is literally translated under translations. So this is minus I O. So this is also exactly the transformation. Now we see that the SOD little group of this particle is in one-to-one correspondence with the SOD representations of the conformal group. So how do we label conformal group? Maybe I should do a bit of a primer in case you don't know. How do you label conformal primary operators? What are the labels of a conformal primary operator? There's delta, and then there's the representation of SOD under which it transforms. We now see that the SOD little group that was showing up in this one particle construction that we had is identified one-to-one with the SOD of the conformal primary. This is what makes massive particles so hard. The little group for massive particles is SOD plus 1. So a single massive particle corresponds to many, many conformal primaries, because you have to take your representation of SOD plus 1 and decompose it into representations of SOD, and you get many representations. For instance, the vector, so a W boson can be decomposed into a massless scalar and a massless photon, that each of these have their own primaries, and you have to do this decomposition for every massive particles, which makes it a bit tedious. But again, can be done, not impossible. Okay, I'm going to write the D, perhaps this is the most important one. It also has exactly the form expected, except for this piece. What is this usually? This is usually a number that we call delta. Usually, when you talk about conformal primaries, on this side you have XA del A plus delta. But we don't have a delta, we have a differential operator, omega del omega. And then similarly, it shouldn't perhaps surprise you that even the Ka action is exactly what we expect. And yet again, in exactly the place where we expect delta, we find omega del omega instead. This is not surprising because we see that under scale transformations, omega is also changing. So of course that should be reflected in the algebra, and it's showing up right over here. So we're almost there. We didn't even have to put in that much effort. We started with a creation operator. That is always what we start with in QFT. All we did is use this slightly clever parametrization for the momentum. And the moment we use this clever parametrization, we already got exactly the right transformation properties, almost, except for this guy. How do we fix this? Yeah, we expand this operator in the set of basis eigenfunctions of this differential operator. What are the basis eigenfunctions of this differential operator? Omega to the minus s. Omega to the s. When you act this differential operator on this, will give you s times omega to the s. So omega to the s are eigenbasis functions of this operator. So all I need to do to construct a conformal primary and is, sorry, come to that. That's it. If I do this, what I mean, perhaps I should have started with the inverse transform, because the idea was to take this and expand it in a basis, but this is a much nicer starting point. But you can now check that the transformation of this, all you have to do is plug this integral in and get it, and show that this transforms exactly like a conformal primary. There's only one question I need to answer, two questions I need to answer. What values of delta? What should I integrate omega over? Okay. There are different answers for both of these questions. In fact, the values of delta are related to the integral contour that I've chosen here. I'm going to tell you just the contour that is standard. There are potentially other contours, but that's a research level problem, and it's still we still don't know whether there are other interesting contours. I'm just going to choose the most natural contour. What is the most natural contour? Omega is energy, so 0 to infinity. Energy is always positive, so all possible energy values just integrate from 0 to infinity. That's it. Yes, good. Infinity. Now this means I need to know the full UV behavior of the theory just to write down these operators. Yes, you do. Celestial amplitudes capture all UV physics of the theory for a single value of delta. If you fix the delta, you have to integrate all the way up to the UV to find the corresponding celestial amplitude, and therefore any celestial amplitude, so I haven't told you what celestial amplitude is. It's just you take a normal scattering matrix and then you do the Mellin transform. What you get is called a celestial amplitude. So celestial amplitudes, by definition, at least by this definition, firstly, you cannot construct them in effective field theory. You somehow need to know the full UV. That's already interesting. But secondly, not only do you need to know the UV, in order for this integral to be well defined, the UV has to be sufficiently soft so that there's no divergences at infinity. And apart from string theory, in any case, apart from string theory, we don't have any known UV complete theory. But at least it's good that in string theory, the UV behavior is exponentially falling off, so these integrals are always well defined for any choice of delta.
I'm a bit confused how to relate this with string theory. I mean,
these amplitudes can be constructed in any theory. They don't have to be constructed in any particular theory. So you give me any S matrix in flat space-time. So I will have to do 10-dimensional string theory, let's say. And I can obviously construct Virasoro, Shapiro, whatever Veneziano amplitude you want. And I can do the Mellin transform of that amplitude. And the point is, at very high energies, those guys all fall off as exponentially fall off. So these integrals will always be well defined. So these are two features that you have to sort of think about. We firstly need to know the UV behavior to even define these things, or assume something about it if we don't know. And secondly, it has to, in order for it to be defined, that UV behavior has to be sufficiently soft.
when you define the creation operator, it does respect to some particular bulk field. And if you go to the UV behavior of the theory, you have no idea what field you have, right?
Yes, that's right. Like if I have confinement as I go, then I don't know what to do about that. These are all great open questions. You can answer them. There are other contours which I much prefer, but those are active papers I'm working on, so I'm not sure if they'll pan out. They might be complete bullshit. But there are other choices of contour so as we'll now see, that this choice of contour will fix delta to be a particular value. You can't have any delta.
Sorry, Rob, just to, again, conceptually not asking the details because of any things related. So I imagine that omega x, the definition of omega x, of the operator, is depending on the energy scale of which I am.
Yeah, this is a creation operator. So this is literally like what you think as A of P.
Yeah, so I imagine that when energies are very high, I have some, say, string vertex that at low energies reduces to
Yeah.
Um,
Yeah, but you can just always do, I mean, if you know your full UV theory,
yeah.
suppose I'm giving that to you, then you can construct an S matrix amplitude for any energies. And you need that input to even compute this integral.
To make meaning of this.
So that's part of the requirement.
So this is telling you, okay, it's not that this is telling you that there should be a UV complete theory.
Well, the way people approach is that let's assume that this is well defined. Let's start by that. And then what features of the amplitude must be true such that this is well defined. And so people work backwards to derive a lot of interesting properties. It has been useful. In fact, it has been shown by Andy itself that there's a lot of interesting, if you assume this is well defined, then in any theory in which this is well defined, you can extract a lot of UV properties by doing IR physics.
Right.
So there's a connection between IR and UV physics in theories, and indeed we know of such connections already in string theory. So even if we didn't know about string theory, just by assuming that whatever theory exists satisfies the property that this is well defined, then you can, just using that, you can derive certain nice, interesting IR versus UV physics connections. Okay. Well, this is not good enough unless I can also invert this. By the way, this is called a Mellin transform. So if you don't know, especially when you integrate from 0 to infinity, this is particularly Mellin transform. It's a very important transformation in number theory and plays a lot of important role in the study of the Riemann zeta function and its relationship to primes. I find that very cool. But for our purposes, I don't care. The main point I'm trying to make is that this transformation, in order for me to say that the celestial amplitudes have just as much information as the S matrix, it has to be invertible. Okay? Indeed, it is invertible. And that's given by what's called the inverse Mellin transform. And the inverse Mellin transform looks like this.
Are you assuming a continuous spectrum?
Yes, you have to. Delta is definitely, the reason it has to be continuous is because I started off with a continuous variable energy, and I'm supplementing that, I'm doing a Mellin transform. So on the other side, I should also have a continuous spectrum. So yes.
Depend usually on the representation of the...
I'm going to tell you soon that this is the principal series representation.
Oh, sorry.
So that is continuous. But I haven't yet fixed H. So the inverse Mellin transform, again, this is Mellin transform theory. I won't really tell you much about it. But the properties of this function over here somehow tells me you can show that this Mellin transform is defined in some interval in complex delta space with some value beta alpha over here. And this integral is defined, and the Mellin transform is analytic inside what's called the Mellin strip. This is the fundamental strip. And this integral over h plus infinity to I infinity is over a contour over here, where in principle h can be chosen to be anything because it's analytic. I can always move it left and right as long as it's inside this strip. And what these alpha and betas are depend on the IR and UV behavior of the S matrix amplitude. So in fact, we do know what this is, but I'm not going to tell you what the details are. Perhaps the only important thing is that d over 2 is in the middle of the strip, which is the principal series. So why particularly d over 2 is going to be the next, I'm going to talk about that soon. Okay, so the idea is now simple. Take your S matrix, which is O omega 1 x1 and do the Mellin transform in all of the omega variables. And consequently, this is by design. So I'm not doing anything fancy right now. It's simply by construction. I'm going to get some quantity that behaves exactly like a conformal, that transforms exactly under the conformal group as a correlation function of local conformal primary operators. Yes?
Sorry, could you comment real quick on these conformally soft limits where delta become
Yeah. So because of the analytic structure in delta, as we'll see, in order for the norm to be finite, we never spoke about the norm yet. We just said we spoke about invertibility. But these have delta function normalizations, which in physics we are okay with. We're happy to have delta function normalizations. So we want to ensure that these guys are also normalizable in the same way. That's what's going to fix h is equal to d over 2. That's how we know it's principal series. However, that being said, so it looks like it should be d over 2 plus I plus minus I infinity all the way. But given the analytic structure in delta, you can perform these integrals on the principal series, and then you can analytically continue the final answer in principle to a large complex delta space. A particular set of deltas that turn out to be super interesting is when delta is 0, minus 1, minus 2, and so on and so forth, these integers. For each of these values of deltas, the S matrix, the celestial amplitude factorizes. Just like soft theorems, where you take a soft limit and there's a factorization. These factorized soft theorems are called conformally soft theorems. They are closely related to the actual soft theorems in momentum space. But more than that, they are closely related to the W1 plus infinity symmetries, which Atul will tell you a lot more about. These operators sitting at these integer values generate the W1 plus infinity algebra. I won't say anything more than that because, in fact, I also don't really know. This is not much of my field, but Atul is, of course, the expert.
You said this x is in this case a momentum variable?
Yes.
So why then the form of the conformal group operators we get, those are the position space form?
For the conformal group.
Yes.
So
so if you showed me that and told me those are conformal transformations, I'd have said x is in position space. That's not.
it is in position space. That's the whole point. There's a localization between momentum space and position space on Scri+.
Position on the sphere.
It is still the localized position on the celestial sphere. This is the localization that makes this really, really nice. Okay, so let's talk about the norm. How much more time? Can I have 10 minutes?
Yes.
Okay.
We talked about the Lorentz transformations, but there are also the translations, right?
Yeah. The bane of my existence. Yeah, I don't know what to do with them. We'll discuss them a little bit, but that's like, yeah, people don't know how to deal with the translations properly. So maybe I can at least tell you what translations does. What is the action of translations on these O's? At least that much I can tell you. And this is the thing that makes it super weird. P0, the Hamiltonian, acting on O delta, gives me O delta plus 1. It shifts delta by 1. Now earlier I told you that this Mellin transform should be defined in a strip, which depends on some properties, blah, blah, blah. Well, now I'm telling you, you define it in a strip, but then I can always shift it with these delta goes to delta plus 1 maps. And I can keep going all the way out to infinity. As much, I can act on it by a million times and take delta goes to delta plus 1,000,000. So not only do you have infinitely many conformal primaries because you have these on the principal series, you have a whole continuum. But in addition to this infinite continuum, because of the translation sector, you also have a discrete infinite continuum. So you start with any delta, and for all delta plus integers, you have all these infinite conformal primaries, and then a continuum on top of them in the plus minus I infinity direction as well. In any case, these are some of the few reasons I'm using the term CCFT, because we don't know of any example of any actual CFT which satisfies all of these properties. But the point that hopefully and this is the goal of my lectures, is that my starting point has always been things that we know everything about, S matrices. And what we are concluding is that if we want to construct CCFTs in the way that we are doing now, these are issues that are present and we have to learn how to deal with. They're not just artifacts they're not just funny things, they're real, and we just have to figure out how to deal with them. And at least as of now, we don't know how to do that. Okay, let me now show that delta lives on the conformal on the principal series. So this is not a hard calculation. I just need to compute the 2-point function. So what is the 2-point function of creation annihilation operators? It's the 1-to-1 scattering amplitude, which is just the delta function, right? So O of P prime, this is 2P0. I'm going to drop factors, additional factors, it's not relevant. Delta D plus 1, P minus P prime. It's a standard 1-to-1 scattering amplitude, which, working it out in these omega x coordinates, which is what I will need, this is 2 to the omega to the d minus 1. Earlier when I wrote it out in 4 dimensions, it was 2 over omega, but now you have extra factors, because just dimensional analysis, honestly. This is delta omega minus omega prime, delta x d x minus x prime. So you can convince yourself that that momentum that I wrote down for you, that momentum parameterization will be used often and often again. So I'll refer to it 100 times. I should probably have written it up there, but hopefully you remember. So that momentum parameterization, you plug it in here, use your usual thing with the Jacobian, and then you get this. Okay, now let's use this to compute O delta x, O delta prime, x prime. Okay, so what do I need to do? 0 to infinity, d omega, 0 to infinity, d omega prime. So these are all the Mellin transform parts. And now I just need to compute the 2-point function of these things, which is given over here. So 2 over omega to the d minus 1 Okay, so this is just a delta function in x minus x prime. It's not playing any role. Let me pull this all the way out. And let's look at the rest of this stuff. So this simple delta function means I can set omega equal to omega prime everywhere. There's a factor of 2 again. There's many factors which I've completely ignored. So you should not trust this overall factor here anyway. And then what's left? What's left is omega delta plus delta prime minus d minus 1. Okay. Now this is the power law, and I'm integrating from 0 to infinity. There's no chance that this is well defined, unless the real part of everything that's inside is 0. That's the only way I can hope that this is well defined. The imaginary part might be something non-zero, and then those oscillations, maybe they'll cancel out. We'll have to figure that out, but in the least, the real part definitely has to cancel out completely. Otherwise, this integral will not be well defined. So it's now clear that we need to take the real part of delta and delta prime, because they're the same operator, to be d over 2. So this integral should be over d over 2. But let's keep going on and now figure out what's the final answer for this entire thing. So to do this, I'm going to take delta as d over 2 plus I nu. That's again, it's standard to call the imaginary part nu. Okay, so let's manipulate this integral. So what I'm going to do here is, in this integral, change coordinates and write omega equal to e to the t. Okay, so I get, now omega is positive, so t is real. So this goes from minus infinity to infinity. Dt e to the, let's see everything that's multiplying t. So there's a factor of 1 that's coming from this measure. So this is t times whatever is inside. Now this d plus delta plus delta prime minus d, when I choose delta to be d over 2, essentially gives me plus I nu plus nu prime. So that's this entire factor here. And then there's a minus 1. Okay, so that integral over t is now dt e to the I nu plus nu prime t. Therefore, delta function nu plus nu prime, and maybe some factors of 2 pi. Okay. In summary, the 2-point function of operators in the CCFT is also super weird. It's clearly not taking the usual form that we are familiar with in a CFT. So O delta of x, O delta prime of x prime is equal to some numbers times. So this nu plus nu prime, it's often convenient, though maybe slightly misleading, but it's often convenient when it's a delta plus delta prime minus d. It's the same thing as that. There's an extra factor of I, but whenever people write this, they really mean nu plus nu prime, but this is a convenient. This 2-point function is consistent with conformal invariance, I claim, despite the fact that what you have been perhaps told or you've derived yourself is that the 2-point function is only non-zero if delta equal to delta prime, and in that case it falls off like a power law, 1 over x to the 2 delta. But that's also consistent.
Because delta function has a weight.
Delta function has weight minus d. And this is fixing delta plus delta prime to be d. So this side has dimension d, this side has dimension d, just as we want. Okay, so I'm going to do one last thing, and I end my lectures. I just realized I'm gone really over time. But one last thing, because I really think this is cool. So everything I did here was for massless particles. And everything that I'm going to do tomorrow is also for massless particles. But I want to write down one formula which, for massive states, just so you know that these things can be generalized. So the idea is the same thing. You start with a massive creation operator. You work out what its Lorentz transformation properties have to be. Now they'll be crazy because SOD plus 1, you have to decompose it into representations of SOD. So in general, it's very complicated. The only case in which it's not complicated is if it's a scalar representation, because then there's exactly 1 degree of freedom, 1 degree of freedom, so you don't have to do anything special. So let's just do it for the scalar degree of freedom. It's still, you will see it's not local in that case. The x coordinate, so the momentum for massive particles, the convenient choice is omega over 2, 1 plus x squared. So you can check that p squared is minus m squared in this case as well. But now this x is not a local coordinate. It does not transform in a local way. However, it transforms in a way that is very geometric. So here's the idea. Suppose I just ask you to find the transformation, find a local operator, construct a local operator from this O. Again, like always, I'm going to follow my nose, and we'll see that it'll just bang on give me the right answer. So what I'm going to start, remember this is p squared equal to minus m squared. This defines a hyperboloid in momentum space, the Euclidean ADS. I'm going to literally think of this as Euclidean ADS. Therefore, the O of p that I have, think of it as a bulk operator in Euclidean ADS. How do I make bulk operators local? You push them out to the boundary. How do you push bulk operators to the boundary? Use the bulk to boundary propagator in ADS. That's all I have to do. So here's the operator that I'll construct that is local. So O of delta x so let's start with k This is the bulk to boundary propagator. Of y. Yeah, yeah. Where this is the usual z over z squared to power delta, z being this. So indeed, m over omega is precisely the radial Poincare, the radial coordinate in Poincare coordinates. So this works. You can now check. I mean, it should be. If you have intuition from ADS, it should be almost obvious. But if I didn't have ADS intuition, it would be very difficult to just guess this. But this absolutely works. So this transforms exactly like a bulk operator in ADS, whose isometries are CFT. We already know that. And we just use the bulk to boundary propagator to map this omega y coordinate, which is a bulk coordinate, to a boundary coordinate x. Using the bulk to boundary propagator, construct this operator. Lo and behold, transforms exactly like a conformal primary at weight delta. So in any case, we can do this, and this is invertible because we know also that in ADS you can go the other way around. So I'll stop here. Thank you. Sorry for going over time.
You get the same principal series condition. for the
Yes,
different
yes, I didn't mention this delta is same for the same norm. You work out the norm, and that's because there's a very nice property about bulk to